the comparison tests. In this section, we'll learn about two other tests that can be used to determine the convergence or divergence of a series. And the first test is called the comparison test, and the second one is called the limit comparison test. So first, the comparison test. Suppose that sum of a sub n and sum of b sub n are series with positive terms. If sum b sub n is convergent and a sub n is less than or equal to b sub n for all n, then sigma sum of a sub n is also convergent. All right, so what is this telling us? So usually with this notation, the way we have this here, the b sub n is some known series, and a sub n is the one we're curious about. So what this first bullet is saying is, if a known series is convergent, and the terms of the series we're curious about, all those terms are less than the terms of the series we know about, then the series we are curious about will also converge. Also, if sigma b sub n is divergent, if the series we know about diverges, and a sub n is greater than or equal to b sub n, and the series and the terms of the series we're curious about are all greater than the terms of the series we know about, then sigma a sub n is also divergent. So if we know a series converges, and another series has terms that are all less than the series we know converges, then the new series must also converge. Also, if we know a series diverges, and we can show that all the terms of the new series are greater than the terms of the series that diverges, then the new series must also diverge. We often will compare to a couple of common series. First, the P series, which we talked about in detail in the last section. We know that sigma 1 over n to the p converges if p is greater than 1 and diverges if p is less than or equal to 1. So we'll often compare to that series. We can also sometimes compare to the geometric series. Remember, that means we have a common ratio, and we know that the geometric series converges if the absolute value of the ratio is less than 1, and it diverges if the absolute value of the ratio is greater than or equal to 1. All right, so now we're going to see how we can use this series, this test. But before we do that, we kind of have to talk a little bit about how fractions compare, because that's an important skill in using the comparison test. All right, so before we continue, suppose x and y are reasonably large numbers, positive numbers. We wish to compare some fractions here. All right, so let's compare. We're looking at the first row here. We want to compare x plus 1 over y to x over y. So in other words, if everything else is held steady, if I increase the numerator by 1, how can I compare the fractions? If I increase the numerator by 1, I get a larger numerator, and if the denominator is held steady, then I would have a greater fraction than the original. Similarly, now looking at the second line, x minus 1 over y. How does that compare to x over y? If I decrease the numerator by 1 and leave the denominator alone, then I have a lesser numerator, and as compared to the original, I would have a lesser fraction. All right, looking at the third row, I have x over y plus 1 as compared to x over y. So now if I increase the denominator of a fraction, what happens? If I increase the denominator, if I have a greater denominator, so let's actually think about some numbers here. So let's say I had 7 over 15. That's my starting fraction. If I increase the denominator, I would get 7 over 16. 7/16 compared to 7/15. If I cut up something into 15 pieces and I take 7 of them, as opposed to if I cut up something into 16 pieces and I take 7 of them, each of those 16 pieces is slightly smaller than each of the 15 pieces. So 7/16 is less than 7/15 and correlates. X over y plus 1 is less than x over y. And using the same sort of argument, x over y minus 1 is greater than x over y. All right, so keep these ideas in mind. They're going to be very useful in this when we deal with this comparison test. So let's see an example of the comparison test. Determine whether the series converges or diverges. And we have sigma n equals 1 to infinity of n minus 1 over n squared times the square root of n. All right, so the first thing I'm going to do is I'm going to try to relate this to some other series. So here's what I would say. First, I'm going to notice that n minus 1 over n squared times the square root of n. What if I could get rid of that 1? How could I compare that to n over n square root n? All right, so if I were to get rid of that 1, now, using what we talked about earlier, n minus 1 over n squared times the square root of n would be less than n times n squared square root of n. So first, we notice that, and that's going to be true for n greater than or equal to 1. Now, let's look at this second series, this n over n squared times the square root of n. The sum from n equals 1 to infinity of n over n squared times the square root of n would be equal to the sum n equals 1 to infinity of n over n to the 2.5, which simplifies as sigma n equals 1 to infinity of 1 over n to the 1.5. Now look at that series. Sigma n equals 1 to infinity of 1 over n to the 1.5 converges. It's a p-series with p greater than 1. So what have we shown? We've shown that the terms of the sequence, right, if we look at that first line, the terms of the sequence are less than the terms of, I'm sorry, I should be careful here. The terms of the series that we're curious about are less than the terms of some other series. And it turns out that that other series converges. So therefore, by the comparison test, sigma n equals 1 to infinity of n minus 1 over n squared times the square root of n converges. We've shown that the terms of the series are less than the terms of some other series. We've shown that that other series converges, so therefore the series we're curious about must converge. Let's consider another example. Sigma n equals 2 to infinity of n cubed over n to the 4th minus 1. And notice that this the series starts with n equals 2. It can't start with n equals 1, because if n equals 1, we have a division by 0. So it starts at n equals 2. All right, so using a similar sort of idea, what I'm going to do here is I'm going to try to think about this series without that 1. All right, so let's notice that n cubed over n to the fourth minus 1. Wait, if I decrease the denominator by 1, it would be greater than n cubed over n to the fourth. And this would be true for n greater than or equal to 2. The sum from n equals, we can start it at 2, doesn't really matter. The sum from n equals 2 to infinity of n cubed over n to the fourth would be equivalent to the sum from n equals 2 to infinity of 1 over n. And we know that sigma 1 over n diverges. Right, that's our old friend, the harmonic series. It's also a p-series with p less than or equal to 1. So however you want to look at it. So what have we done? We've shown that the terms of this series are greater than the terms of some other series. And it turns out that that other series simplifies to the harmonic series, which diverges. So we're comparing to a diverging series, and all of the terms of the series we're curious about are greater than that diverging series. So therefore, sigma n equals 2 to infinity of n cubed over n to the fourth minus 1 diverges by comparison. All right, here's another example. This would be a good time for you to pause and try this one out on your own. All right, so here we're asked to determine if the series converges or diverges, and we have sigma n equals 2 to infinity of root n over n minus 1. All right, so I'm going to first notice that the square root of n over n minus 1 would be greater than the square root of n over n for n greater than or equal to 2. And sigma n equals 2 to infinity of root n over n is the same as sigma n equals 2 to infinity of, let's see, that would be 0.5 over 1. So that would be 1 over n to the 0.5, which diverges. This is a p-series with p less than or equal to 1. In this case, it's less than. So therefore, sigma n equals 2 to infinity of root n over n minus 1 diverges by comparison. The terms of the series we are curious about are greater than the terms of this other series. The other series diverges, so therefore the series we're curious about diverges by comparison. Now the limit comparison test. Suppose that sigma a sub n and sigma b sub n are series with positive terms. Now usually the a sub n, that's the one we're curious about, and the sigma b sub n is known. So suppose that these are series with positive terms. then what we can do is we can look at the limit of a sub n over b sub n as n approaches infinity, and it breaks down into several cases. If the limit as n approaches infinity of a sub n over b sub n is equal to c, which is some positive number, then either both series converge or both diverge. So if we know that sigma b sub n converges, then the sigma a sub n must also converge. If the limit as n approaches infinity of a sub n over b sub n is 0 and b sub n converges, then a sub n must also converge. If the limit as n approaches infinity of a sub n over b sub n is infinite and sigma b sub n diverges, then sigma a sub n also diverges. So now we're going to look at a few examples. Again, the question is determine whether the series converges or diverges. And here we have sigma n equals 1 to infinity of 1 over 2n plus 3. You might say, well, can we just use the comparison test? Well, what would we do? Well, if we had 1 over 2n plus 3, notice that that would be less than 1 over 2n. And so if I were to think, okay, well, if I were to look at sigma 1 over 2n, that's 1/2 of sigma 1 over n. So why can't I use the comparison test? I mean, I know that this will diverge, right? I know that 1/2 sigma 1 over n diverges, but wait a second. For this to work, if to use the standard comparison test, I want 1 over 2n plus 3, I would want that to be a greater than. So I can't use the straight comparison test here. It just doesn't work. So let's start over and let's try a new test. So now I'm going to try the limit comparison test. So I see that 1 over 2n plus 3, I see that 1 over n, right? I see that 1 over n. I'm going to try to compare. So I'm going to, let's be more careful. I'm going to limit compare to sigma 1 over n, which I know diverges. All right, so to apply the limit comparison test, what I do is I evaluate the limit with n approaching infinity. Now, this is my a sub n, and this is my b sub n. So, limit as n approaches infinity of 1 over 2n plus 3 over 1 over n. A little bit of algebra here. That's the limit as n approaches infinity of n over 2n plus 3. Well, that is a indeterminate form. That's infinity over infinity. So I will apply L'Hopital's rule here. I'm going to treat this illegally as a function. Okay, it's really, since it's n's, I should rewrite this in terms of x's. I'm not going to be as careful here. Applying L'Hopital's rule, limit n approaching infinity of 1 over 2. And so that would be 1/2. All right, so this is that first condition on the previous slide. So notice that first condition says, if the limit as n approaches infinity of a sub n over b sub n is c, which is greater than 0, that's what we have right now. Our c value is 1/2. Then either both series converge or both diverge. So what I can say here is that since limit as n approaches infinity of a sub n over b sub n is equal to 1/2, and sigma n equals 1 to infinity of b sub n diverges, then sigma n equals 1 to infinity of 1 over 2n plus 3 also diverges. So there's an example of the use of the limit comparison test. Let's see another example. Determine whether the series converges or diverges, and here we have sigma n equals 1 to infinity of n plus 2 over n plus 1 cubed. All right, so we're increasing the numerator, we're increasing the denominator. It would be difficult to find a straight comparison here. But what I do notice is that the numerator is of degree 1 and the denominator is of degree 2. So what I'm going to try is a limit comparison. I'm going to limit compare to sigma n equals 1 to infinity of n over n cubed, or sigma n equals 1 to infinity of 1 over n squared. Now, I know that this converges because it's a p-series with p greater than 1. So let's keep that in mind. All right, limit comparison test. So I would take the limit with n approaching infinity of a sub n, that would be n plus 2 over n plus 1 cubed, over 1 over n squared. So this becomes the limit, n approaching infinity, a little bit of algebra here. I would have n squared by n plus 2 over n plus 1 cubed. All right, a little bit more algebra. That's the limit, n approaching infinity, of a distributed property, n cubed plus 2n squared. The denominator, n plus 1 cubed, means n plus 1 times n plus 1 times n plus 1, and go through the multiplication here, either using Pascal's triangle or the binomial theorem, and you get n cubed plus 3n squared plus 3n plus 1. Now, if we apply, so this is an indeterminate form, if we apply L'Hopital's rule several times, we find that this limit, this becomes the limit as n approaches infinity, and you would end up with 3 over 3, which is 1. So, limit as n approaches infinity of a sub n over b sub n is 1, and sigma n equals 1 to infinity of b sub n converges. And so again, that's that first case that we saw on that slide. The limit is greater than 0, and since sigma b sub n converges, and so sigma n equals 1 to infinity of n plus 2 over n plus 1 cubed also converges. All right, and here's a third example. And now would be a good time to pause and try this one out on your own. All right, so here we have sigma n equals 2 to infinity of 1 over n times the square root of n squared minus 1. And again, notice it starts at n equals 2 because if we allowed it to start at n equals 1, our first term would be undefined. So we have it start at 2. This was a little bit tougher. It's not as clear what we should compare to. But, what if I just kind of got rid of the 1 here? I'm going to limit compare to sigma n equals 2 to infinity of 1 over n times the square root of n. And I should say square root of n squared. And since n is positive, I can write that as n equals 2 to infinity of, well, the square root of n squared will be n, since n is positive, and so that's 1 over n squared, which again, we know converges. All right, so now I'm going to apply the limit comparison test. So I would take the limit with n approaching infinity, 1 over n, square root of n squared minus 1, over 1 over n squared. Okay, so then this becomes the limit, n approaching infinity, of, let's see, that would give me an n squared over n times the square root of n squared minus 1. And we can remove that common factor of n. And so that would be n over the square root of n squared minus 1. All right, so now this is an indeterminate form. I could apply L'Hopital's rule. I don't know necessarily that's a good idea. So instead, what I'll do is use a simpler technique that you should have learned in a Calculus 1 course. I'll divide both numerator and denominator by the square root of n squared. I say, well, that's just n. Yes, but now, since I've written it as the square root of n squared, I can combine those radicals in the denominator. And so then this becomes the limit with n approaching infinity. Now the numerator is just going to be 1. The denominator is going to be the square root of n squared minus 1 over n squared, which simplifies as the limit, n approaching infinity, 1 over the square root of 1 minus 1 over n squared. And now I can easily let n approach infinity, and so as n approaches infinity, this becomes 1 over the square root of 1 minus 0, which is 1. So the limit at infinity of a sub n over b sub n is 1. And sigma n equals 1 to, well, 2 to infinity at least, of b sub n, which is 1 over n squared, converges. So sigma n equals 2 to infinity of 1 over n times the square root of n squared minus 1 also converges. All right, that concludes this presentation.